Thank you for the introduction. I'm Gennaro Bellizzi, can you hear me? And I'm a postdoc fellow at Erasmus MC in Rotterdam. And today I'm going to present you basically the state of the art, so the rationale behind the development of our MR-guided applicator for head and neck carcinoma, the MRcollar. Some hint on the design, which was done by Thomas. You heard him speaking yesterday. And some first results from the experimental validation, which is currently being carried out by Kemal, PhD student, with my help. And I'm going to give you the state of the art in the development for the MR integration of the system. So first of all, MR guided. Why? Because temperature monitoring is temperature matters, as we heard, and temperature monitoring is nowadays performed with invasive probes, which are often unfeasible and uncomfortable for the patient, and mostly they only provide limited information on the temperature that we are inducing in the patient. So we only have temperature measurement at the tip of the probe. But MR thermometry was shown to be suitable for monitoring the temperature, and it allows us to have a 3D distribution of the temperature. So we have a clear view of the treatment that we are administering to the patient, and it is a non-invasive monitoring, so we can exploit it without problems theoretically. However, what we see is that accurateness of MR thermometry is limited in the head and neck by motion. And what we see here is that basically without any heating, without performing any heating, if we perform MR thermometry, we see that there is an apparent temperature change due to respiration. Plus we have swallowing, plus we have motion of the patient itself. So we need to have accurate monitoring of the thermometry, and to do so we need fast scanning, fast sequences to overcome the limitation of breathing, swallowing, and motion of the patient. And nowadays, like technology that is well known, is that we need to have high signal to noise ratio, and this can be achieved by have close to skin receiver coils. So what was the challenge in developing the MRcollar? To integrate the best of today's practice. So to integrate receiver coil, close to skin receiver coil for MR imaging within our clinically used Hypercollar 3D, which is the applicator that we are currently using at Erasmus MC for head and neck carcinoma. So we started from Hypercollar 3D, and this is made by 20 patch antennas. And patch antennas, they have a shield, which they have a background, like a PEC background, which is basically shielding the patient within the MR. So this is not MR compatible. So first thing we did is to develop a lab prototype with the same patch antennas, but without by shrinking the background, the PEC. And we validated the possibility of using 434 to heat and to monitor, and these are and to steer the heating focus, and this was achieved by the body coil. So these MR thermometry are not done with the close to skin receiver coil, but with the body coil. Starting from these first preliminary good results, Martin Paulidis came up with a novel antenna design, which is this printed antenna, this printed diag antenna, which is being printed. It allows is highly reproducible. It can allow to handle high power. Plus, it has a minimal impact on the MR imaging, and it can be used to be geometrically decoupled from a receiver coil. So I will show you now how Thomas designed it in order to have the Yagi antenna for heating geometrically decoupled by the receiver coil for MR imaging. So by inserting, by decoupled MR and hyperthermia insert, the MRcollar was designed and prototyped as you can see here. This is, yeah. So these are it's made by 12 of those the Yagi antenna I just showed you, and the Yagi antenna are geometrically decoupled with a receiver coil which are round, and the applicator includes this purple and yellow tube, which are fat references for MR thermometry. The applicator was prototyped, and I want to point out that by integrating two different systems, one for heating and one for imaging, we can this allow us the degrees of freedom on the choice of the frequency for heating and for imaging. So in this way, we can still use 434, which allow us to have target conformal heating and to use this system in whatever available MR scanner, just by developing tailored coils for that scanner. What I'm going to show you now is just the result about the validation of the system, the MR compatibility of the system, and the heating. We validated the heating and the steering capabilities of applicator. And I'm going to give you some hint at the end of what is basically my main business at the moment, which is the development and integration of the coil within the applicator. So first results, we tested the steering capabilities of the applicator. We were able to have an increase of 7 degrees in 3 minutes with 180 forward power. We validated also that we can steer the focus, so in the X, in the Z direction, and these are measurements done with the infrared camera in a split phantom. So that's a phantom which can be opened in 2 halves, and with the infrared camera we measure the temperature induced in the central plane. And we didn't use any treatment planning here because we wanted to measure also and to see what is the actual focus size that we can generate with the applicator. So we use time reversal. And so the second hotspot, the secondary spot that you see, this is approximately a lambda, which is as predicted from theory with time reversal. Second of all, we validated the MR compatibility of the device. So we imaged the phantom only. A second setup including the phantom and the MRcollar. And what you see here is the water system which is needed to cool the antenna down. And then a third setup where we are imaging the phantom with the MRcollar plus the water bolus, which you see here. And what we see is that there is no qualitative drop in image quality. That there is a minimal impact of the metallic part due to the antenna, which was also shown in the preliminary paper where we developed the antenna. And that what we found out with this last measurement is that the major impact on the image quality is given by the water bolus, probably due to energy absorption. So meaning that we need to have a thinner water bolus with this applicator. And lastly, I want to give you some hints of what is being done now. We want to integrate a 6+1 coil array within the applicator, and those need to be tailored for the specific application because we have very high and strict space requirements. And 6+1 because we want to integrate 3 for each shell plus 1 on the headrest. And this is the first prototype I did for 1.5 Tesla, and it was developed according to GE safety standard, including 2 different safety aperture for the coil in order not to get skin burns to the patient, balance matching to have stability with different loads, and a cable balloon to avoid standing current on the outside of the coaxial cable, which also can generate burns to the patient. So, in conclusion, we validated the MR compatibility and the steering capabilities of the newly prototype MRcollar, and the integration and test of a dedicated MR receiver coil for accurate MR thermometry. I hope I will be presenting this at ICO 2020 next year in Rotterdam. And thank you for your attention.